So we have a question in our assignment, and the question gives you a certain pressure. The question gives you a certain refrigerant that you're going to be using, and then the question gives you a certain temperature that you need to use. So when it comes time to working out subcooling and superheating, we follow a methodical procedure. We follow a certain method. Okay, so I'm going to use an example where we are measuring a pressure of, our pressure is, change the color, so high pressure side. So our pressure is 10 bar gauge. Okay, I have 10 bar gauge from my gauge. My so that's my pressure. My temperature is telling me, my temperature sensor is telling me plus 32 degrees Celsius. And in my system I have R134A. Okay, so I need to know what the pressure is. I then have my R134A tables that I use, and that will give me the temperature along that line, my saturation temperature. Okay, that's the process, that's the procedure we follow for all of these questions, all of these. And in practical, I go and measure my high pressure on my condenser side, I measure the temperature of my pipe leaving my condenser, I put this all on a piece of paper, and I say to myself, yes, my system is working correctly, or no, I need to clean the condenser, or perhaps I have not enough refrigerant in my system. So this is where we're heading towards, is to be able to understand the operation of a refrigeration system. Okay, so the pressure was 10 bar gauge. From previous slide we said that pressure absolute is equal to pressure gauge plus 1. So I need to go to my vapor tables with my 11 bar gauge. Okay, I take out my vapor tables, I look down the pressure column until I find 11 or the closest number, and that is giving me 43 degrees Celsius. Okay, so that's the temperature here inside my condenser, the condensing temperature. Then I have measured leaving my condenser the temperature of plus 32 degrees. So I say to myself, is 32 warmer or colder than 43? Well, it's colder, so do I go up or do I go down? It's a reducing temperature going down on the chart. So I'm going to plot somewhere there. It doesn't matter how far down, I'm just going down my 32. And if I go across, the only place I get to is subcooled liquid. That's the only line that I'm actually crossing with my measured temperature. So how much subcooling have we got? It's the difference between these two numbers. The answer is we definitely have subcooled liquid, and the value is 43 minus 32 gives me 11 degrees of subcooling. Now, theoretically we should say 11 Kelvin, but we could say 11 degrees Celsius. Okay. So, yeah. But practically speaking, my system has got 11 degrees of subcooling. And I'm happy. I'm not going to touch it. I'm going to leave it alone. It's working fine. Okay, so the procedure again. We get given a pressure from a pressure gauge. We get given a temperature from a temperature sensor. We get told what refrigerant there is in the system by means of looking at the manufacturer's plate or labels on components, or the system itself, manufacturer's manual. We then take out a piece of paper and we draw our chart. On the chart we plot the information we have. Our pressure must be a pressure absolute. And with the pressure we go to our vapor table, and from the vapor table we get the corresponding saturation temperature. We then compare the temperature we've measured with the temperature we found. If it's warmer, we go up. If it's colder, we go down. The temperature we found is colder, so we go down, we plot it, and we find that we have a certain amount of subcooling. That's great. Okay, so in any case, from experience and industry, subcooling in the region of 3 to about 5 degrees is desirable. That would be the desirable value. So we've got a little bit of overcooling going on there. Not a train smash, but also it could lead to problems on bigger systems. Different kinds of systems can suffer from overcooling on the condenser side. But if this is just a small split wall air conditioning unit, and it's a hermetically sealed compressor, and it's an outdoor unit, and it's on the cold side of the building away from the sun, man, I'm going to leave it alone. Okay, let's move on. So, low pressure and superheating. So, see, I got a mistake here in the slide. Alright, so let's fix that quickly while I can. The low pressure gauge. To the low pressure side. This is the problem with copy and paste and working late at night. And then blue gauge, blue hose. Okay. So the temperature sensor will be applied to the outlet of the evaporator. Even my spelling is getting bad now. Alright, so the temperature sensor applied to the outlet pipe of the evaporator. So here would come my temperature sensor, measuring the temperature leaving the evaporator, and my low pressure gauge fitted to the suction service valve of my refrigeration system to give me the pressure. So there's my low pressure, and it's going to be a gauge pressure. Okay, so remember that low pressure exists everywhere in the system. So here we have our low pressure, and the low pressure is telling me about the saturation temperature. In fact, if we take it a step further, that saturation temperature exists from that point, from the point leaving the expansion valve all the way through to where we run out of liquid. Okay. So the problem is now on the low pressure side to calculate the low pressure side. So we're going to be operating a freezing room. So the freezing room temperature minus 18 degrees Celsius. Okay, so the freezer is minus 18 degrees Celsius. We get given the suction pressure from a gauge, pressure gauge. One comma 27 bar. Okay, so we get given our pressure is pressure gauge 1,27 bar. We were given the temperature measured after the evaporator of minus 17 degrees Celsius, and in this case we are dealing with R22. So I need to know what my saturation temperature is. So that's the temperature there. To find out the saturation temperature, I need to know what refrigerant I'm dealing with. And we said 22. And I need to know what my saturation pressure is. And that must be an absolute value. So pressure gauge plus 1 gives me 227 bar absolute. Okay, and going to my 22 tables, R22 tables with 2,27 gives me minus 22 degrees Celsius. Okay, so minus 22 is the temperature happening inside our evaporator. But hang on, they're telling us that we are measuring minus 17 leaving the evaporator. Now on the face of it, that's a smaller number, so it should be colder. But if you look carefully, we're dealing with negative numbers, minus numbers. So we have to ask ourselves, is minus 17 warmer or colder than minus 22? And simply the answer is no. Minus 17 is warmer than minus 22. So we actually have to go up. So the temperature leaving the evaporator will either be the same or warmer than the saturation temperature in the evaporator. Okay, so the saturation temperature or warmer, meaning we're going to be going up. And the temperature they gave us being minus 17 degrees Celsius. And if I just do a line across here, I get there, and I'm having superheated vapor on that part of the graph. How much superheat have we got? It's the difference between these two numbers. Okay, so the superheat value is equal to 22 minus 17, and that's going to give me 5 degrees. Okay, 5 degrees of superheat. So 5 Kelvin or 5 degrees Celsius superheat. And that's perfect. It's good enough. Alright. So we can safely say that our system on the low pressure side is working just fine. There's no need for any invasive testing or checking or taking things apart. I might go and eyeball the evaporator. I might go and see how the cold room is packed to see that it is being efficiently packed. I might just go and listen to the noise the evaporator fan's making to see if the bearings are okay. Other than that, I'm not going to touch the system. Industry superheat value for refrigeration system. Superheat value 3 to 5 degrees. Okay. For air cons though, it's a bit different because an air conditioner, the evaporator is not in a temperature controlled environment. So that means an evaporator for an air con is in a room where there's zero insulation. There might be windows, there might be sunshine, there might be computers. A whole group of people can walk in at one moment and then a whole group can leave the next moment. Could even have heaters, kettle or something affecting it. So the heat energy for an aircon is very variable. So the heat energy is required to cause the refrigerant to change from a liquid to a vapor. So if that heat energy suddenly disappears, it means there's no heat energy and our liquid does not stay liquid. Our liquid will stay liquid, and that liquid in the saturated mixture would then pass into the suction of the compressor. So the compressor would become damaged. So the superheat value is higher for an aircon system simply because of the variable heat energy changes that could occur, and to allow the machine time, the components to allow them time to compensate. So we normally deal with 15 degrees around about there of superheat for aircons. And again, it doesn't really matter how big the system is. You're applying the same theory and the same numbers. Okay, so that's our desired superheat value. For refrigeration or aircon systems. Okay, so it's been a really rather long lecture. There has been some mistakes and this computer's been giving me a hell of a hard time with trying to present stuff. So just bear with it please until we get back to class, and we can deal with it then. So in any case, I hope you've learned and that you're able to deal with assignment number 3 a little bit better. We're going to make a day of it to do this practical once we get back to class. So you please do the assignment, try it, get it done, submit it, and so that I can check it out, and then we can plan at a later date when we're back in class to do the practicals. Okay. In any case, the summary of this module, we looked at sensible heat and latent heat energy transfer, and sensible heat causes a temperature change, and latent heat causes a change of state or phase change. We need the temperature enthalpy chart to work out whether a substance would be subcooled, saturated, or superheated. Okay. We looked at the vapor compression system again, the 4 main components. You could say the refrigerant is the 5th main component. Vapor compression cycle is plotted on a temperature, pressure enthalpy chart. refrigerant properties we need to be concerned with is the specific pressure-temperature relationship for working out these subcooled, superheated or saturated values. And then using the vapor tables, you can get the corresponding saturation pressure temperature relationships. Okay, so to do that you would need a pressure and you would need a temperature, and that you're getting from instruments, your pressure measuring instruments and your temperature measuring instruments. We're going to use a temperature enthalpy chart for the high pressure side separately from a temperature enthalpy chart for the low pressure side. Okay, when you become more experienced and you become more used to looking at these things, you'll be able to work it out by just looking at the gauges and then looking at your instruments and then working it out in your head. But for now, put it down on paper. You need pressure gauges and you need temperature instruments, otherwise it's a waste of time. So to measure your pressures and your temperatures. Okay. So that's it for now. Hope this helps, and you can send me an email or a message via the Moodle site to complete this. Okay.